Okay, in this lecture video, we're going to talk about competitive inhibitors. So competitive inhibition of enzyme activity. And so in this case, we're talking about a molecule or an inhibitor I that competes for binding to the active site. So it competes for active site with the enzyme's natural substrate. So it's trying to bind to that enzyme first. So what happens is when the inhibitor binds to the active site, no chemistry happens. It just sits there, but it's basically blocking that active site from binding to the substrate. So what we're talking about in our regular schematic for enzymes reacting with substrates, they form an enzyme-substrate complex and then form product. But in the presence of a competitive inhibitor, we're looking at this case where now there's a competition taking place, so enzyme plus inhibitor going to form this enzyme inhibitor complex. So this enzyme is being torn in both directions. So when we look at it, competitive inhibitors are going to have a distinct effect on the Km, the binding affinity for substrate, because they're essentially blocking the enzyme's active site where the inhibitor is going to bind. So we know that we could talk about the dissociation constant for the enzyme inhibitor complex, right? And that's called the Ki. So that's the dissociation constant that describes the affinity of the inhibitor for that particular enzyme. So we can tell from this that the higher the Ki, the worse the affinity. So the higher the Ki, the worse that inhibitor is. It's not as good at its job of being an inhibitor. So now let's look at how this affects the binding parameters. So V0 then equals Vmax times the concentration of S. But now what we're affecting directly is the Km for that enzyme. So I'm going to put alpha Km here, which describes how the Km has been modified. So alpha is this factor in the presence of enzyme that has now changed the value for the Km. So alpha is equal to 1 plus the concentration of Ki over, the concentration of Ki, that doesn't make sense. 1 plus the concentration of inhibitor over the Ki value. So you can calculate alpha and Ki and see how good your inhibitor is. In terms of what that looks like on a Michaelis-Menten plot, if this is the concentration of substrate and this is the initial reaction velocity, here it is in the absence of inhibitor. In the presence of inhibitor, that graph is going to look like this. So the question is, how can you overcome competitive inhibition? So if we look at this graph, we've seen that Km has moved the position of half Vmax, right? So if this is Vmax, then this would be Vmax over 2. So we can see that the Km value has now shifted in the presence of the inhibitor. But eventually, even in the presence of inhibitor, this red graph is going to eventually make its way up to Vmax. So if you add lots and lots of substrate, eventually you will have a scenario where the enzyme will have a higher probability of finding substrate rather than an inhibitor. So you can essentially outcompete your competitive inhibitor in the presence of lots of substrate. So what we see going on here is in the presence of a competitive inhibitor, Vmax is unchanged, right? Because eventually you can get to Vmax if you add enough substrate. However, the Km for that enzyme is increased. And we can see that here on the graph. It now takes more substrate to get to half the maximum velocity in the presence of inhibitor. So we now see how these two parameters change in the presence of a competitive inhibitor. And this is important because we can do experiments. When we've discovered a new inhibitor, we can do experiments and see whether or not the Vmax of that enzyme is unchanged, but the Km goes up. And if it does, then we can start classifying the mechanism of action of that particular inhibitor molecule as competitive. And we would do that with a double reciprocal plot. So we've got 1 over V0, we've got 1 over the concentration of substrate. So if I were to show what it looks like, oops, that's horrible. It's really hard to draw a straight line freehand on a computer like this. Okay, so we know that this position is 1 over Vmax. And going this way from experiment 1, experiment 2, experiment 3, we are increasing the concentration of inhibitor. So here we would have no inhibitor, and then in experiment 2 we would have some inhibitor, and in experiment 3 we would have more inhibitor. And what we see is since they're all intersecting on the y-axis, which is the location of 1 over Vmax, then we know that Vmax is not changing. We also know that these positions here, this one, and this one, those are minus 1 over the Km value. So let's be clear, this is experiment 1, this is experiment 2, this is experiment 3. So what we see is as we add more inhibitor, going from left to right here along the x-axis, as we add more inhibitor, we see a decrease in the value of 1 over Km. Therefore, that means that Km itself is going up in order for this number to be getting smaller. So that's what we expect for competitive inhibition. So we would do these experiments where we're varying the amount of inhibitor we have, make a double reciprocal plot, and see, does Vmax stay the same, and does Km increase? If so, then that particular inhibitor would be classified as a competitive inhibitor. And it's likely that we would already have an idea about that based on the structure of that particular molecule, because what we saw even in our nuts and bolts activity is that competitive inhibitors are structurally similar to the substrate molecule, and even more particularly the transition state of that substrate molecule. That's why they are able to be effective competitors to bind to the active site of the enzyme.